In this video, we're going over the practice test for geometry. So when you do this test, you should have this test along with the circle theorem sheet here. Okay, so really important, we need to look at what performance standards we're being marked on. This first one here, CT1, means basically, can you do the maths? Like, do you know what you're doing, essentially? Then this next one is notation. The one under that is reasoning. So really important for this reasoning one is, can you explain everything you're doing? And the last one is development and testing of valid conjectures. So that means you're making predictions about circles in this test, and then you're testing those predictions. Okay. So let's make a start. It's really important that you give full reasoning for every answer. And that's because of that RC4 performance standard that we saw before, the reasoning and communication one. So this one tells you to use angle in a semicircle theorem. So that's exactly what we're going to do. We're going to do angle BCD equals 90 degrees by angle in a semicircle theorem. So we'll mark that on. Therefore, 52 plus 90 plus this missing angle ABC equals 180 by sum of angles in triangle CBD. Therefore, well, 52 plus 90 is 142 plus the angle ABC equals 180. So angle ABC equals 180, take 142, which I believe should give you 38 degrees. All right, suppose that is 4 BC and CD is 5. Let's find the radius. So BD, the length squared, equals BC squared plus CD squared. So BD squared, and this just comes from Pythagoras, equals 4 squared plus 5 squared. So BD squared equals 16 plus 25, which is 41. So BD equals root 41, which approximately equals, we can check our answer here. .403. So it asks for the radius though. So AB equals half BD, which is the radius. So that's 6.403 divided by 2. Because what we found before was the diameter, 3.202. Notice how I've used the full answer. So 6.403, if you halve that, it doesn't look like you get 3.202, but once you bring the rounding into play, you actually do. All right, in the diagram alongside, you're going to use the angle between a tangent and a chord theorem to find the angle labeled as x. So we're going to find this angle here, 23 plus 71 plus our angle ABC, all has to equal 180 by a sum of angles in triangle ABC. Therefore, angle ABC equals, well, 180 is going to be take 94, which is 86. So let's just check that all that checks out. So if I do 23 plus 71, I get 94. And if I do 180 take 94, I should get 86. Beautiful. So that's 86. Therefore, x equals 86 by angle between tangent and chord theorem. So that theorem tells you basically that that angle there and that angle there are the same. All right, beautiful. Next one. In the circle alongside, A is the center and CBD is 140, find CAD. So this doesn't tell you the theorem. This is actually angle at the center theorem, and it's sort of like this special case sitting right here. So let's have a go. We're going to go angle CAD external equals 2 times 140 by angle at center equals 280. So that there is 280. Therefore, x plus 280 equals 360 by angles at a point. Therefore, x would have to be 80 degrees. All right, cool. In this one, we're going to find the angle GCE using angles subtended by the same arc. So this is the angle we're looking for, and it's literally just the same. Angle GCE equals GBD by angles subtended by same arc, which equals 37 degrees. Suppose BGD is 124. So suppose that angle there is 124. What we want to find is CEG. So we want to find that angle in there. Well, okay. Therefore, CGE equals 124 by vertically opposite angles. 24. Therefore, 37 plus 124 plus our mystery angle, angle CEG, equals 180. And this is sum of angles in triangle CEG. All right, so that's 37 plus 124. We'll see what that is. $161. Therefore, the angle CEG equals 19. Beautiful. So there's a couple of ways you could go about that. The other way you could do it is you could find this angle in here first. You would find that that's 19, and then you just use angles subtended by the same arc again. So there's a few methods to get there. All right, this one. Find the missing angle. This probably looks like subtended by the same arc, but it's actually angles at the center. Because if you have the same arc, they have to all touch the edges, and this one does not touch the edge at point A. So, angle DBC equals half of angle DAC by angles at center. So if we look at our angle at the center theorem, it looks kind of like this special case here. Equals half of 54, which is 27. All right, in this diagram, BC is tangent to the circle, A is the center, and BAC is 51. Find the angle BCA, labeled as C. So first thing we need to do is note that angle ABC equals 90 degrees by, that will be the radius tangent theorem. Where's our radius tangent theorem? Yeah. So if you have a tangent and it goes into the radius, that makes 90 degrees. So mark that in. Therefore, 51 plus 90 plus C equals 180. Therefore, 141 plus C equals 180. Therefore, C, I think, has to be 39 degrees. Let's double check that. 51 plus 90. 180, take 141. Sure is 39. All right, BCD is a cyclic quadrilateral. Find the angle BED. There it is. So we know angle BED plus angle DCB equals 180 degrees by cyclic quad BCDE. So you know that the opposite angles have to add up to 180. So therefore angle BED plus 70 equals 180. Therefore angle BED equals 110. Also, really important, make sure you've got degrees on everything and you've got really clear notation, because as I showed you before, one of the performance standards you're being marked on at the top is accurate use of notation. I will ding you if you miss your notation stuff here. All right. This one, question 6. So we've got this situation here. We want to find the angle of the bad angle. All right, so basically what we need to do is radius tangent theorem twice. So that angle and that angle are both 90. So angle ABC and angle ADC equal 90 degrees by radius tangent theorem. All right, so that's great. Then we have 40, A plus 90 plus 90 plus 43, all those four angles would have to equal 360 by sum of angles in a quadrilateral. The quadrilateral is ABCD. So A plus 223 equals 360. Okay, so let's see. 360 take 223. $137. Beautiful. 137. All right, then you're spotting patterns, okay? So this is making a conjecture, and it's really important that you can do this because there's a whole performance standard on developing and testing conjectures. And that keyword there, develop. We need to develop a conjecture to hit that performance standard. So this is probably the most important question on the test in terms of performance standards, because your grade is based on performance standards, not marks. All right. So make a conjecture about the values A and C. Well, what do we notice? We're looking for patterns here. Have a think about what you notice about those two numbers. Hopefully you spot the A plus C should always add up to 180 degrees. And I think that's the case for our one up here, 137 and 43. Yeah, that does give you 180 as well. So when you're looking for these patterns, you're looking maybe for, is something doubled from something else? Do they add up to something? Are they related in some way? And that's the way. All right, so use your conjecture to predict the value of C if A equals 100. Well, we know A plus C equals 180. Therefore, 100 plus C equals 180. Therefore, C equals 80 degrees. All right. The points A, B, C, D are joined to form a quadrilateral in all the pictures above. So the quadrilateral is just that. Is it possible to draw a circle around this quadrilateral which perfectly touches all 4 points? So that seems like a really weird question. And what it's actually asking about is cyclic quadrilaterals. So if you look at your theorem sheet, we got this. 4 points are said to be concyclic if a circle can be drawn through them, and they're called a cyclic quadrilateral. So basically, the question in a roundabout way is asking, is this quadrilateral here a cyclic quadrilateral? Now, we do already have a circle in the picture, but that's not the circle we're talking about. We're talking about the circle that can be drawn around that quadrilateral. Okay, so is it? Well, here's how we test. We test, do the opposite angles add up to 180 degrees? And yes. Yes. ABCD is a cyclic quadrilateral because opposite angles add up to 180 degrees. Therefore, a circle can be drawn around it. Beautiful. And touch all points. Next, it's known that CB equals 10 centimeters, so that is the whole length being 10, and ODB equals 90 degrees. Find the length of CB. So what we've got here is a situation like in the chord of a circle theorem, just here. So if you have a right angle, it splits the chord perfectly. Or alternatively, if it splits the chord perfectly, you know you have a right angle. So we got the right angle. So CD equals DB equals half of the total length by chord of a circle theorem. Therefore, CD equals a half of 10, which is 5 centimeters. So let's label that in 5. If the circle above has a radius of 15 centimeters, calculate the length of AD. Okay, so we'll do that. The radius is 15 centimeters. And so we have a situation like this where we've got a triangle and we've got 5 centimeters along there, 15 centimeters along there, and we've got a right angle. Then we label this triangle as C, B, and A, and C squared equals A squared plus B squared based on Pythagoras. All right, so 15 squared equals A squared plus 5 squared. 15 squared, I believe, is 225. 225 equals A squared plus 25. Therefore, take 25 from both sides, you get 200 equals A squared. So A equals square root of 200. So A equals 14.142 centimeters. Okay, so then that means this length up here is 14.142 centimeters, but that's not the length they're asking for. They're actually asking for the length A to D. So A to D plus DO equals, well, A to O, which is the radius. Therefore, AD plus DO would have to be 15, because 15 was the radius. We know what A to D, we know what D to O already is. AD plus 14.142 would have to equal 15. So AD equals 15, take 14.142. And we'll see what we get here. 15, take our answer that we just got. It's going to be 0.858 centimeters. Notice I've used the squiggly equal sign. That's because I've rounded. That's really important for your notation. All right, in the circle alongside, CE equals 4 and ED equals 12. We want to find the length of CB. Let's just call it X. So let CB equal X. And then this theorem that we have, we're basically going to be using the secant tangent theorem. So the length squared equals the other two lengths times together. So secant tangent theorem says x squared equals 4 times by the whole length across there, which is 16. You have to be really careful. Don't do 4 times 12. It's 4 times the whole length, which is 16. So x squared equals, well, 4 times 16. is 64. Therefore, x equals square root of 64. Therefore, x equals 8 centimeters. Just double check that. Square root of 64 does indeed give you 8. So there you go. Technically, my interpretation, I should have had secant tangent theorem out there and said x squared equals 4 times 16 by the secant tangent theorem. All right. Last one is a proof, and it's really important that you have got this question, even if you can do a little bit. I want to note as well, with these questions, it's quite often you can do the later part without doing the earlier part. So question 6, suppose you didn't get this part A. In part B, well, you can still make the conjecture if you can spot the pattern in the circles above, right? And you can still predict the value if you, yeah. So you can always do the later parts if you couldn't get the earlier parts. Part A, make sure you don't miss this, is to draw a line connecting the point A with point B. And it wants you to label the point A, B, C as P and A, B, D as Q. And that will get you the mark there, so make sure you actually do that. Explain why the two triangles BAD and BAC are isosceles, because AC and AB are equal, because radius. Therefore, triangle ABC is isosceles. And then AB and AD are equal because it's a radius. Therefore, triangle BAD is isosceles. Both of them are isosceles. Hence, find the angles BCA and BDA in terms of P and Q. Angle BCA is supposed to equal angle ABC by isosceles. Triangle BAC. That should have been BAC there because it was what they actually asked us to show. Which both equal P. So basically you're going to put P in there. Similarly, angle ADB equals Q by isosceles triangle BAD Q. Hence find the angles that and that. So basically angle CAB plus P equals 180 degrees by sum of angles in triangle BAC. Therefore, angle CAB equals 180 take 2P. We'll mark that in. And then BAD plus Q equals 180, sum of angles in triangle BAD. Therefore, angle BAD equals 180 take 2Q. All right. Because you've done sum of angles in each of the little triangles there. All right, hence solve the semicircle, prove the, I've given the wrong theorem now. Anyway, it's going to be hence prove the angle in the center theorem. Try to show that x equals 2p plus 2q. So basically what you want to do is angles around a point. So you're going to say 180 take 2p plus 180 take 2q plus x should all equal 360 by angles around a point. Therefore, 360 plus x take 2p take 2q equals 360. Then you want to take 360 from both sides. That will essentially cancel those off. Your x take 2p take 2q equals 0. Therefore, x equals 2p plus 2q. Just adding 2p and 2q onto both sides. Now, you can say, like, take 360 from both, plus 2p plus 2q from both. Just to be really clear when you're proving this theorem. Therefore, x is going to be 2 lots of p plus q, which is 2 lots of the angle CBD. And we proved our theorem. We can draw a little box or say as required or something like that. Beautiful. That's the test done. So yeah, make sure a big thing here is notation and explanation, because if you look at the actual mass itself, you're only being marked that basically 1/4 of your grade. The rest all comes from that notation and stuff.